So my name is Alex Minnaar. I'm a research engineer here at Nitro, and my talk is about, my talk's about using word vectors to evaluate the human interpretability of topic models. So this is just a lightning talk, so I might not go as in-depth into some concepts as I probably should, but I'm available after if you have questions. Topic models are a collection of unsupervised learning algorithms that try to uncover the hidden latent thematic structure of large document collections. So they can be very useful for tasks such as searching and browsing and summarizing these large document collections. And the most popular topic modeling algorithm is Latent Dirichlet Allocation, or LDA. So just at a high level, LDA represents topics as distributions over words and represents documents as distributions over topics. So here's an illustration of LDA here. So on the left you have your global topic distributions, and here's an example document in a corpus. It has a local document proportions distribution, and each word is assumed to be generated by a topic, which is, or sampled from a topic, which is sampled from the document's topic distribution. Right, so LDA has a free parameter k, which determines the number of topics to be learned. And often if k is chosen to be too small or too large, the topics can be of poor quality. And here's an example of a good topic and a bad topic. And it should be obvious why the good topic is good, it's human interpretable, and the bad topic is not. So in order to choose the optimal k, we have to have a way to evaluate a topic model. And LDA is an unsupervised learning algorithm, so that's not straightforward at all. So early on, people had been using statistical evaluation techniques. So basically what they did was they got their corpus and they divided into a training set and a test set. And they trained their LDA model on the training set, and then they computed the predictive likelihood on the test set given the parameters that were learned in the training set. So the idea being that a model that is able to predict a set of held out documents well would be a high quality model, and vice versa. But this was sort of contradicted in a paper in 2009 called Reading Tea Leaves, How Humans Interpret Topic Models. And basically, this paper described an experiment. So it was a large-scale Amazon Mechanical Turk experiment where a topic model was learned. And then the top 5 words by probability for each topic were taken, and a 6th intruder word, a random word, was added to each of these topics. And then the Turkers were asked to try to identify that intruder word. So if the Turkers were able to consistently find that random intruder word, then this means that the topic is human interpretable, because obviously the topic words contain some sort of thematic coherence, so it would be easy to pick out the random one, and vice versa. So the surprising result was that topics that had a high predictive likelihood were not correlated with topics that were shown to be human interpretable, and in some cases they were actually anti-correlated. So this result caused people to sort of move away from the predictive likelihood evaluation metric and move towards trying to evaluate topic models by trying to model this human interpretability. So the intuition is that topics whose high probability words that are semantically similar to each other should be topics that are human interpretable, and vice versa. So this sort of topic coherence general formula was created. So basically you take the high probability words within a topic, and then compute the pairwise semantic similarity between each pair. So there were a few papers that did this, one using point-wise mutual information to assess the semantic similarity between the words, one using WordNet. So basically if two words fell under the same WordNet concept, then they were said to be semantically similar. And so this sort of topic coherence approach performed much better in the word intrusion task than predictive likelihood. So sort of the main point of this talk is how to use word vectors to compute topic coherence. So basically just a broad overview of word vectors. So they're produced from unsupervised neural network models that are fed large amounts of unstructured text data, and these vector representations of words are produced, and these vector representations capture the semantic information of the corresponding word. So it turns out that if you take the cosine similarity between these word vectors, it's an effective measure of the semantic similarity between the corresponding words. So for example, if you Google provides some pre-trained word vectors using the word-to-vec algorithms. And if you look at the word vector corresponding to the word France, the most similar words, according to cosine similarity, are the ones you see here. So words like Spain, Belgium, Netherlands, ones we know, are in fact semantically similar. So basically we use the same idea, just to take the high probability words within the topic and then compute the average pairwise cosine similarity between the corresponding word vectors. So to the best of our knowledge, this approach hasn't been tried before. So we haven't yet applied this to the word intrusion task, but we have tried this with our own corpus that we ran an LDA model on. So we ran a 100-topic LDA model, and then we computed the topic coherence for each of the resulting topics. And on the left are the top 5 topics by word vector coherence, and on the right are the bottom 5. And I think you can agree that the topics on the left are much more human interpretable than the ones on the right. Right, and this also, this topic coherence idea can have extensions to the online LDA algorithm. So basically the online LDA algorithm learns the topics in a sequential manner. So basically many batches of documents are fed into the model, and the topics are updated in this way, rather than in batch with regular LDA. So one of the benefits of online LDA is that we could actually see how the topics are changing after each mini batch. So if we can see how the topics are changing, we can also see how the topic coherence is changing. And it's interesting to see how this actually works. I mean, our intuition should be that the coherence should increase as we see more mini batches. The idea being the more data you see, the more coherent your topic should be. So we tried this experiment, and this was the result. So as you can see, on average there is a coherence increase, but it's definitely not monotonic. In fact, some mini batches actually decrease the overall coherence. So each data point here is the average coherence over all the topics learned. So even though there could be an increase in coherence on average, there still could be some decreases in coherence in some topics. So this sort of gave us the idea of what if we could sort of simply track the most coherent version of each topic that we've seen so far, and basically only update it if the next mini batch increases the coherence of that topic. So this led us to this sort of greedy coherence online LDA. And so that green line there shows sort of these greedy topics that are monotonically increasing in coherence by design. And as you can see, at the end, we end up with a set of topics that are much more coherent than if we had just run online LDA normally. That's it. Sure. Yeah. So for that last part, so we're actually not influencing the model with that. So basically, we're just running we're basically just running the online LDA normally. It's just in the background. We're just keeping track of the most coherent version of the topic that we've seen so far. So we let it run normally, but we just sort of record the most coherent, and we basically don't update that version unless we see a more coherent version. So we're not actually influencing the algorithm at all. No, no. Yep. Yeah, so you'd have to have in memory the current topic and the most coherent topic so far, so it's double the memory. Yeah, it was trained on the corpus. Yeah. Yep. Good question. So it was trained on about 30,000 documents, I believe. Yeah. Yeah.
Would it perhaps interesting to modify the LDA algorithm so that it prefers coherent topics to just any topics? Did you think about that?
Yeah, that's a good idea. I mean, I've read previous papers where they've done this with Gibbs sampling. They've sort of biased the probability of sampling words that are semantically similar to each other. But yeah, if I had more time, I'd like to explore that. Yep. Well, we're actually not, we're not sort of changing the original algorithm at all. We're just sort of keeping track of the most coherent ones we've seen so far. So we're not actually replacing we're actually not updating the actual topics that are being learned. We're just keeping in the background sort of the best ones that have been seen so far. Yeah. Yep.
Can you try a baseline where you simply select subset of optimize that subset?
Sorry, can you repeat that?
Just like take a subset of you just partition the vocabulary or you selecting a subset where they optimize their usage.
Yeah.
Like a base, I mean, you don't even bother with the whole LDA
I'm not sure. I'd have to think about that. We could talk later. Good.